Very good afternoon, everyone. I am Susank Chigilipalli, an undergraduate student from the Department of Civil Engineering at IIT Kharagpur, and Summer Research Intern at Maritime Research Center, Pune. I'm working on open pond agriculture demographic mapping using computer vision and satellite imagery. Hmm. This is the content of the presentation. Motivation. Mangrove forests sequester carbon much faster than other forests, so they are vital in fight against the climate change. When mangroves are degraded or lost due to costly aquaculture, particularly shrimp farming, the release stored carbon stock back into the atmosphere, thus significantly contributing to the greenhouse gas emission. Nutrient transport due to this clearing of mangroves to adjacent ecosystems like oceans causes biodiversity loss, such as seagrass meadows and coral reefs, and also exacerbates the climatic variables. This extensive clearing of not only mangroves but also the agricultural land led to the conflict between agriculture and shrimp farming, resulting in land and water degradation. This shift has affected traditional livelihoods and employment opportunities of locals, as aquaculture is less labor intensive compared to agriculture. Despite these efforts, aquaculture play a vital role in food security. So it is crucial to find balance through sustainable practices. This requires identifying suitable land for aquaculture and tracking aquaculture demographic changes in the landscape to enhance spatial planning. Our area of study focus on the area encompassed between coastline and 200-kilometer inland from the coastline. For our study, we use Sentinel-2 data because due to its high spatial resolution. With other data sources like OpenStreetMap, digital elevation model from NASA, and shape parameter dataset. Our study focuses on identification of filled and unfilled ponds, demarcating them, calculating cumulative area of agriculture ponds for spatiotemporal analysis, and finding the coordinates and converting them into geographic latitude and longitude coordinates for accurate marine spatial planning, and also tracking spatiotemporal changes for sustainable aquaculture management. So this is the methodology on how we identify filled and unfilled ponds using normalized difference water index and image processing techniques. We started with collecting Sentinel-2 data, focusing on the red, infrared, and shortwave infrared bands, which are crucial for distinguishing water bodies from other land features. Next, we calculated NDWI using green and near infrared bands. Um, uh, this enhances the visibility of water bodies in the imagery. Uh, then we did image segmentation with DeepLab v3. This accurately segments water bodies in our image. This model helps us to identify and isolate the water bodies from surrounding land. So after segmentation, we proceeded to post-processing and shape feature extraction. We refine our segmented images using morphological operations and extract shape features like area, perimeter, and the ratio, compactness, and centroid. These features are vital for understanding the characteristics of each one. When these when we use these shape features to train the random forest classifier, this classifier helps us to distinguish between the aquaculture ponds and natural ponds with some good accuracy. Once classified, we extract the centroid coordinates of each pond. This involves identifying the latitude and longitude of the centroid, providing precise location data. And then we perform NDWI based confirmation. We revisit the centroid coordinates of the NDWI image to verify the classification based on the predefined NDWI threshold. This step ensures that our classification is accurate and reliable. Uh, tracking spatial temporal changes. Uh, Tracking spatial temporal distribution is an interval-based study with several critical steps. First, studying aquaculture ponds over by past 30 years. Then we set specific time window from April to October each year, aligning with peak vegetation growth and pond culturing activities for optimal satellite imagery identification. Next, sorting images by the cloud cover attribute and prioritizing them with minimal cloud cover. We manually inspect these images to ensure clarity. We used a decision tree classifier for pond identification, which quantifies changes in aquaculture ponds and reviews significant trends over time. We calculate dynamic indicators such as holding area change rate and cumulative area change rates and transfer out rates to understand the expansion, shrinkage, and overall impacts of natural wetland and mangroves. Finally, we analyze these trends to uncover the effects of pollution, climate change, and urbanization on the coastal aquaculture. This comprehensive analysis supports sustainable practices and long-term ecological health. So, for estimating longevity and age of aquaculture ponds, we follow a structured approach. First, we observe the initial and final appearances of each pond. Based on some rules, we split the data into periods. Next, we extract temporal features from the time series data, including changes in area and shape and other spectral signatures. We also consider the duration of filling and drying cycles and variations in surrounding vegetation. We use temporal convolution networks for their ability to hand sequence data and capture long-range dependencies. Training the TCN model with historical data helps us to predict the future state of the pond and estimate their lifespan. This method provides a detailed understanding of the dynamics of aquaculture pond, aiding in better management and conservation strategies. So, optical satellite imagery, which is crucial for NDWA calculation, can be heavily affected by the cloud cover, reducing the availability of clear images. Frequent cloud cover could lead to significant temporal gaps in data and make it difficult to track changes over time accurately. Developing and training machine learning model such as decision tree or decision tree for accurate classification of pond requires some large shape feature data, well-labeled shape feature data, which is not readily available. So, applications. Our study helps in real-time monitoring, in assessment of non-human impacts, and directly helps in spatial planning for sustainable agriculture management. Future works like identification of abandoned aquaculture ponds for revegetation and conservation of mangroves, and also optimization of aquaculture site selection. This can be done with integration of new data sources and technologies and other improved analytical methods. This is a quote from Dan Barber. Aquaculture needs to balance the scale of economic growth and environmental stewardship. This emphasizes on the sustainable aquaculture management. Thank you, and once again, wish everyone a very good afternoon.